So negative 2 times R1, that's going to give me a negative 4 plus 4 is 0. A negative 6 plus 13 is 7. A negative 4 plus 9 is 5. We do the same thing, but with a 6, which gives me a 0, 14, 10. So we're going to start building L after we do that. Right? So we have our main diagonal and everything below it that are going to be numerical. Everything above our main diagonal is going to contain zeros. That's the lower triangular. That means all of the numerical non-zero values will be in the lower triangular portion of the matrix. Upper triangular means that all of the entries will be in the upper triangular portion. All right, so we're building this towards becoming a U by starting to zero out all the entries below the main diagonal, and this we're assuming all the entries above the main diagonal are equal to 0. Right? So once we've developed the structure of L, row reduced the original matrix in such a way that we're zeroing out the first column, we go back to the original and divide each entry by whatever the pivot number was. Now, a nice little outcome here is whatever numbers you use to perform those elementary row operations, those are going to be the numbers that make up the entries in your column, right? Because I needed a negative 2. I'm sorry, well, those would be the absolute numbers. So I needed a negative 2 to zero this out. So if I take this number, divide it by 2, I get a 2. So you actually just reverse the signs. But, you know, you could actually just obviously perform the division too. So it's kind of looking for a mnemonic where it's not necessary. So 4 divided by 2, well, actually 2 divided by 2 is 1. 4 divided by 2 is 2. And then negative 6 divided by 2 is negative 3. All right. So then in the next progression, or next part of the progression, I'm working to my second column. First column's good to go now, because it's not a reduced row echelon, it's just echelon. So I need the entry below the 7 to become a 0. I can do that. Negative 2 times R2 plus R3. Zeros out. All right. You definitely want to combine your steps when you're reducing each column down to zeros. Have it so that each matrix, in order to keep things organized, each matrix is, or each successive matrix is the culmination of all those operations. Because what we're doing is we're always looking at, for the first column, the entries in the first column, we'll look at the first matrix that we have. For the second column, we're going to look at the second matrix that we have. And for the third column, we'll look at the third matrix. So that progression kind of flows nicely if you keep it organized.
When you were building L, how do you get the first column again?
First column we get by taking each entry in our original matrix and dividing it by the pivot number.
Okay.
So in this matrix, we're going to take, ignoring anything that's in the upper triangle, those zeros, we're going to take all the relevant values, divide them by the pivot number. So my pivot number here is a 7. And again, it's technically not necessary that we carry down this step in order to figure out the second column. But in theory, it's like, well, how do we truly know the 7 is the pivot number until we get it into echelon form? It's the first non-zero entry in row 2. So that's the pivot number. So that brings me back here where I say, okay, based on this pivot number, what are the multipliers that would get me this? We'll keep it at 7 and then move it to 14. Right? So basically anything at the pivot and below, divide by the pivot. Right? So
Was your pivot 2 or for the first one?
for the first one, it was 2.
So you circled the purple?
Oh, because I was emphasizing that as the reason why I came up with the 2,
Oh.
but it's irrelevant now. It was an in the moment kind of thing. All right, so 14 divided by 7 is 2. 7 divided by itself is 1. If it were a 4 by 4, 5 by 5, we would continue on, but it's in echelon form. So now for the final entry, all I need is, well, normally I would say pivot divided by itself, but it's not a pivot. Right, there is no pivot, so we're going to put a 0 in there for that. Negative 3. All right. That's not what I want. Bring that up. Let me just. Do that. All right, so that last bit there, that 0 component, that's the only part that might be a little kooky because it's like, well, you're just going to throw the 0 there? Well, the answer is, well, yeah, for 2 reasons. One of them makes more sense than the other, but the idea is that if we follow the algorithm of dividing a number by a pivot, you get 0 over 0, which is indeterminate. That would screw up everything, right? So that's the one reason that it doesn't really have any kind of basis in reality. The other piece or component is that we should have pivot numbers occupying the main diagonal. Right? So if there is an entry in the main diagonal anywhere, whether it's a 1 or something other than 1, then it is considered to be a pivot value, assuming that the other values that are around it are 0. Right? So by putting something in this along the main diagonal, we're claiming that it is a pivot number. But I'm telling you, in my row reduction of U, that it is not, because we have an entire row of zeros. So there are no pivots in row 3. So why would we be claiming that there was a pivot of any non-zero entry in row 3, column 3? Right? It wouldn't make sense to do that because there is no pivot. Right? So that's the more, or the less just because explanation. Let's put it that way.
On the test, you have to show that check.
Oh, only for your own benefit. Like I said a few times, sometimes that works against you for the peace of mind factor. Like if I screwed, like something bigger, if I screwed it up, I don't think I want to know. Just move on and go home. Worry about it down the line. Although the algorithm, it works even for more complicated situations. It's just you do have to carry out the row reduction part of it. So in the part where we're building U, and you could organize it any way you want. Oh.
Calculator program written for this?
Do I? No. Not yet. It's on my list of things to do. I'm sure somebody does that.
I mean, I've been thinking about how to do it, but like, it's really hard because you can't just tell the calculator to put it into reduced row echelon
Because of the row swapping component, yeah.
that you don't really want it in reduced row echelon.
That has essentially been my problem. Okay, so I'm going to zero out all the entries below 1 in column 1. So multiply by -5, then by 2, then by +115. And then add the other entries that make this any kind of amount of work. So 5, 1, 6. 0 would be 5. That would be 1 and 6 again. Next up is red. And then 0, 10, 2, 12. Also known as 0516 times 2. Alright, so we'll have our entries along the main diagonal. Above those entries would be the 0 entries. We can't assume one's along the main diagonal because of the previous example. I mean, if you were taking a gamble, it's a pretty good gamble to put ones along the main diagonal, but it's not always going to play out. Right? So column 1 goes to the first matrix. Divide each entry by the pivot. So 5, -2, -1. So actually, as it turns out, column 1 in my L will be the same as it was in the original. Now I have to zero out the entries below row 2, column 2. So the 5 and the 10 have to go away. So negative R2 plus R3. Negative 2R2 plus R4. Then all zeros, right? Right, because columns 3 and 4 are just multiples of, I'm sorry, columns 3 and 4. Rows 3 and 4 are multiples of row 2. which means that they're just essentially the same linear equation if it's a line, or plane, or whatever. In this case, that's a plane. So that's going to be fun in a second. Good fun, I think. In this case here, we're going to take each of the entries below the pivot and divide it by the pivot itself. So 10 divided by 5, 2, 5 divided by 5, 1, and then again. So 1, 1, 2, down the line. And then a whole lot of zeros to finish it up. All right, because there's nothing else to do. No pivot values, so zeros along those diagonals. And then that's it. Okay. All right, so we have our L and we have our U, and then we call it a day.